morning everybody. I am Preethi from CS department. I am going to handle a video lecture on multiprocessor and thread level parallelism. Here in this video lecture, the main objective is parallel computer, the classification based on memory and synchronization and memory consistency model. So, in the parallel computer, why we are going for the parallel computer is, so every operations and everywhere we are using the web pages and simultaneous access in all the applications. So, for that purpose we are going for the multiprocessor. When we use a single processor, so we cannot get the improved performance and availability of the data. So, for that purpose we are going for the multiprocessor. And again another thing is, here we are discussing about the thread level parallelism. Why we are moved for thread level parallelism is, the instruction level parallelism, the performance is very less, the latency also very high. To avoid the problem, we are going for the thread level parallelism. And here the parallel computers can be discussed with the two techniques. First one is based on the Fink's taxonomy, the second one is based on the memory. Based on the memory management, here we are having the two classifications, one is symmetric architecture, another one is distributed architecture. Then we are going to discuss about what is synchronizations, what are the issues can be developed in the synchronization. Then we are going to discuss about what is memory consistency. Here the Fink's taxonomy, we are having a four classification. The first one is single instruction, single data. The example is uniprocessor. Here only single processor can be used. The second one is single instruction, multiple data. Here the example is vector and CM2. The third one is multiple instruction, single data. And fourth one is multiple instruction, multiple data. The example is clusters and SMP servers. So, this is the things. And the single instruction, single data, only a single operations and single data can be handled. Here the single instructions, multiple data is, multiple data can be handled by the single instructions. The example is EDOC and CM2. The advantages we are going to list over it can be there. And next one is multiple instructions, multiple data. The multiple instructions, multiple data, here each processor can have own instructions and it can operate on the data. The advantages flexible and user cutoff can be there. And why we are going for the MIMD architecture is, here everywhere we are using the multiple instruction. For example, the web page, and if you want to see the result data also, we need many persons are working on to see the same data. At that time we are using the multiple instruction single data and multiple instruction multiple data. So, it is very flexible. And the major styles of MIMD processor is the centralized shared memory and decentralized shared memory. The centralized shared memory, we are having the uniform memory access, and the shared memory architecture can be used. So, what are the main applications? Why we are going for the multiprocessors? So, this is the things. First one is database servers. So, because large amount of data can be handled. When we have to handle large amount of data, single processor cannot be enough to catch all the data. So, if you want to download the data also, it is very tedious task. So, for that purpose we are using the multiprocessor. And next one is web servers and web page applications. So, all the web commerce and web page applications, online shopping, and if you want to download the anonymous results, everywhere we are using the multiprocessor applications. And third one is compilers. If you want to handle a large amount of data, can be the compilers, and the data centers also, they need the multiprocessor. And next one is multimedia application. Nowadays the video and audio files are very important, because if you want to download the movie applications, if you want to send the message and voice data, we need the parallel operations can be needed. At the same time, many person downloading the same data, same movies and all, we need a multimedia application. And next one is scientific applications, because the many weather forecasting and data mining applications, everywhere we are using the multiprocessor. And the military purpose also we are using the multiprocessor. And next one is thread level parallelism applications, because here the single program can be executed parallelly and the data can be taken. For here why we are going for the thread level parallelism is, we are having the parallelism in terms of ILP, DLP and TLP. ILP, here the instructions can be executed parallelly, but we can get more disadvantages and the performance is very less. And the DLP also, the data can be executed in parallelly. But why thread level parallelism is very important is, here everywhere every applications single program or single task can be taken and it can be executed. So the classes of the multiprocessor, two types of multiprocessors can be there. One is centralized processor, another one is a distributed processor. The centralized processor, we are having a single common memory can be used. The distributed processor, every processor can have the single memory, and a separate cache also can be there. So this is the architecture. So in the centralized architecture, we are having a single memory, and each processor 1, processor 2, processor 3 can be extended. Each processor can have a separate cache memory. And the distributed processor, there is no common memory can be there. Here every processor can have a single cache memory, and we are having the interconnection network, and a separate memory also can be there. There is no common memory can be there in the distributed processor. So what is the centralized memory multiprocessor? Why we are going for the centralized memory multiprocessor is, the centralized memory multiprocessor, otherwise called as SMP processor, symmetric multiprocessor also. Here we are having a common memory, and every processor want to take a data, means it has to take a data from the memory, and it can be placed in the cache memory, and the processor can perform the operations. After performing the operations, every processor has to update the cache memory also, main memory also. Otherwise, cache coherence problems can be arised. And here we are having the large caches, okay, because why we are needing the cache memory is, frequently accessed instructions can be stored in the cache memory. Every time if you want to take a data to the main memory is a tedious task, so the cache memory can be used. So whatever data can be in the main memory, the same copy or a partial copy can be present in the cache memory. And the cache memory also can be extended in terms of levels of cache, level 1 cache, level 2 cache, and level 3 cache. And if suppose the x is the value can be taken, x is equal to 10 value can be taken from the main memory, it can be taken for P1, P2, etc. Pn. If you want to update the P1 processor, for example, x is updated, means after updation of x value has to be updated to the main memory, otherwise the cache coherent problems can be used. And if you want to extend the cache also, it is also possible with the use of large level 1, level 2 cache, and the switch also possible. If suppose I want to take a data from the process 1 to process 2, here the data dependency problem also can be raised. And the scaling beyond, if you want to increase the scaling also, we prefer the multiprocessor centralized processor. And why we are, what is the distributed memory? The distributed memory, there is no common memory can be there. Why we are going for the distributed memory is, here the cost effective, because every time if you want to extend a large memory is a tedious task. To avoid the things, every processor can have a separate memory. And another advantage is reduce their latency of local memory. What are disadvantages is, here communication is very difficult, because all the processor can communicate, can have a separate memory within the processor. If suppose the process 1, process 2, process 3 want to communicate between the process, a tedious task. The communication is very difficult task. If suppose any problems can be arise in the communication, is a problem in the distributed architecture. And another thing is, here we are having the changes software. Every time we want to scaling and changing is very important. And next one is, here what are the things can be there in the distributed architecture is message passing communications. Here there is no, because the processor 1 can have the same, x is the value is equal to 10 can be used by the processor P1, P2, P3. P1 wants to update with the x plus plus, and P2 wants to update with the value of x minus minus, and P3 is x, means every time every processor wants to update to the another processor with the use of messages. Message is very important. The communication message passing mechanisms used in the distributed architecture. And another, here we are having the two types of time slots can be there. The first one is UMA, uniform memory access time. The second one is non-uniform memory access time. So every time how much time can be taken to take a data from the main memory to the cache memory, or every processor between the memory and cache memory is uniform. That is the things can be there. And here we are having the, what are the challenges of this parallel processing? The first one is application parallelism, because all the data can be shared between the processor. The data shared means definitely we can get a problem, because one processor can handle the data, at the same time another processor also want to access the data. Definitely the problem can be arised. Otherwise the same data can be handled by the lakhs and lakhs of the people also, we can get the problem. definitely we can get the problem. If you want to download any data, common data from the website also, we can get the problem. That is the application level parallelism problems can be raised. That is a very important challenge in the multiprocessor. The second one is can be the local remote latency effect, because the latency is very, very important, because whenever the processor can be nearer to the locations, can get the data easily. But whenever the data can be a very large distance, means very difficult, because we are using a distributed architecture, because everywhere, because here also we are using, India also we are using, Australia also we are using, USA also we are using, and the people's normal people's also using, the layman also using. So every person using the common data, means definitely the latency is very, very important, because if suppose educated people can get the data easily, but uneducated people want to search and search again and get the data. At the time we can get the latency impact in the parallel processing. So how to reduce that problem is with the use of catching the shared data and the restructuring the data. And next one is symmetric shared architecture. Here when we have discussed about the symmetric shared architecture. The symmetric shared architecture, we are using the common memory. Okay, when we use a common memory and every processor have a separate cache memory, every time the cache wants to update the data in the main memory, that is very, very important. If suppose if it is not updated properly, we can get a problem. Okay, and that is the thing. So sometimes we can use the private data, there is no problem. Sometimes we are using the shared data, because the X value can be updated in both places, P1 also, P2 also, P3, means the same X value can be shared by the processor. Definitely we can get the problem. And next one is when the same data can be handled by the different processor, at some time we cannot get the data. So there is a stalling also can be there in the multiprocessor. So there is a cache coherence problem, because already I told about this. This is a processor P1, this is the processor P2, this is the processor P3. Here we are asking the memory. The memory we are having the data. I already told here I am having the data U is equal to 5. 5 is the data can be used. It's a common memory data. It can be used by the processor P1, and it can be used with the processor P2, and it can be used with the processor P3. So here the P1 the data can be decremented. P1 value is 4, and P2 the same data can be handled. The P3 we are using the data is U is equal to U plus 2. Okay, so what is the problem? So the P1 contains U value is 4, the P2 contains U value is 5, and P3 contains U value is 7. So every processor can have a different value for the same variable. So that is the cache coherence problem. So because this is the even to 1 and this is even 2, this is even 3. How to solve the problem is, here we are going to two things we are going to use. When we use the processor P1, has to issue the write invalidate. Okay, the write invalidate message, and after that, after processing the P1 or P2, it has to issue the write update. When we issue the write update protocol, so all the processor can be updated. That is the very, very important one. So the write back cache also very, very essential. So we have the write back caches, and we are going to issue the write invalidate and write update. So that is the memory model of the distributed architecture and symmetric and distributed architecture. Here we are having the cache, and we are having the memory and disk. The secondary memory details also we can use with the use of disk, CDs and all. And the memory we are having the common data. Already I told about the cache memory contains what are the data can be present in the main memory. The same data can be present in the cache memory. If suppose the main memory is very, very larger means, but the cache memory is smaller means, we can extend the cache memory. How it is means, it is a level 1 and level 2 cache. So level 1 cache and the cache is near the processor or within the processor can be present. So the cache memory is very small when compared to the main memory. So we can increase the cache memory with the use of level 1 and level cache. And two important issues can be there in the cache memory. First one is coherence issues and second one is consistency issues. What is coherence? For example, here what are different values can be read by the processor, then we can get a coherence problem. For example, already we have discussed in the previous slide, u value can be different. U value is main memory, we are having the u value is 5, the cache the processor within the cache we are having u value is 4, 5 and 7. So when we read the values, we can get the different values for the u. For that problem is called as cache coherence problem. What is the cache consistency problem? Is nothing but whenever the write value can be issued, the recent write value only we need, because the read and write can be performed within the memory and processor. That is very, very important. So the recent write is very, very important. Otherwise we can get the consistency problem. The first one is coherence problem, another one is a consistency problem. So this is the cache coherency. Here we are having three different things. The first one is preserve the program order. So because when the processor use the data, we are having the first we are issuing one read value and after that we are issuing one write value. Between the read and write, we have to check what is the recent write value to be taken. That is very, very important, because there is a things can be given. Always return the recent write value by the processor. So that property is called as preserve program order. The second one is coherent view of the memory, because between the read and write processor, the time is very, very important, and the time separations can be needed between read and write. If suppose one value can be read by the particular processor, so another processor wants to write the value base, the processor has to wait for the previous read to complete. Read after write, that is RAW things can be there. And next one is write serialization, because if suppose two writes to be performed by the two processor, the first processor writes some value for the particular variable, same variable, the second processor wants to update the same variable also. It has to, the two serialization is very, very important. The first write after completing the second write, which is the last write, that is the updated value. Write update is very, very important. And next one is basic scheme of imposing the coherence. Here we are having the two different things can be there. One is migration, another one is replication, because already we have discussed about in the cache we can get the consistency problem and coherence problem. How the consistency and coherence problems can be solved with the use of migration and replication. Migration is nothing but moving the data, already we know. Here also we are moving the data to the local cache, that is the things can be there. Local cache we are moving the data. Second one is replications of the cache. So what is replication is duplications. We are copying the same data in the multiple places. The cache data also can be copied and it can be placed at the some other location. So these two techniques can be used to enforcing the coherence problem. The coherence problems can be solved with the use of two techniques. First one is migration technique, second one is replication technique. And next one is two classes of cache coherence protocols, because already I told the cache coherence is a very, very important issue. So what is the issues is the processor reads the value, the same value, the same accessing value can be different in the two processor. P1 contains one value u is equal to 4 and P2 contains another value u is equal to 5 for our example, and another processor contains the variable u is equal to 7. So we are having the same variable, but each variable that values can be different. That is the cache coherence problem. So the cache coherence problems can be solved with the use of Snoopy protocol. We are having the two different protocols can be used. The first one is directory based protocol, another one is a snooping protocol. The directory based protocol, here other than main memory and cache memory, we are having the physical memory data can be in one place. That place is called as a directory. With the use of directory, we are going to get a messages between the main memory and cache memory and the processor. Another one is a snooping. Snooping is nothing but monitor. The snooping meaning is monitor. We are going to monitor what are the transactions can be present between the processor, main memory and cache memory. That is the things can be there. So here we are having the, because the cache data can be traversed between the buses and switches can be used, and the and again that how it can be monitored means with the use of cache controller. The cache controller monitor can be used. That is called the snoop, can be used to monitor what are the the data can be taken from the main memory to the cache memory and cache memory to the processor after processing all the instruction from the arithmetic and logic unit, and it can be given to the cache memory. After that, the cache memory wants to update to the main memory. The updation is very, very important. The right update is very, very important to solve the cache coherence problem. So this is the cache coherence problem, and here already I told the cache controller snoops. Snoops is nothing but monitor what are the transactions can be present in the system. So when we monitor the things, easily we can identify whether which is the recent write, which is the recent read, and all the operations can be monitored. And here the transaction is very important, whether it can be the cache transaction or processor transaction or main memory transactions. So here we are having the exclusive access or shared access. Exclusive access means we can perform read or write operations. Shared means only the read operations can be performed. So what are the protocols can be used is, so first one is write through invalidate. So already the problem has been discussed already, how the problem can be solved. For that purpose we are having the write through invalidate, because the processor P1 accesses the data, okay, u is equal to 5. If the processor P3 want to update, the processor P3 want to update the data means it issues the invalidate to the processor P1. Then it update the data. After update, the processor P3 updated, it issue the write update. Write update means, so all the processor can be updated the values. So here we are having the 4 and 5, the 7, already I told all the things. So here how we are going to issue the write invalidate is, if suppose P3 wants to update the data, it issue the invalidate to P1 and P2. After completing the operations, the P3 issues update on the P1 and P2. So that is called as write invalidate protocol. So it invalidate all the processor. After the process completed, it issues a write update to the all the processor. So that protocol is called as write through invalidate. So here for that purpose we are having the finite state machine. The finite state machine, each cache contains extra bit. That bit is called as invalidate bit, valid bit and dati bit. To see the block changes can be there. And here the broadcast medium is bus. Already we know the bus is a communication device. With the use of bus only, all the data can be transferred between the main memory to the cache memory and cache memory to the processor, and the processor to the cache memory, and the cache memory to the remaining processor and the main memory also. And that is the things here. Already the write serialization is very, very important, because for enforcing the cache coherence problem, the write serialization is very, very important. So for that purpose only we are using the write invalidate and write update. So here the cache, how the interference can be avoided within the cache coherence problem. The first one is we are using the cache address tags can be used to avoid the things. The second one is to reduce the inference, we are using the duplicating the tags. The tags can be duplicated. And third one is, already I told, we are having the cache, the level 1 cache, level 2 cache and level 3 cache, because every time the level 1 cache can be, it can be used widely. So to avoid the problem, we are increasing the level 2 cache and level 3 cache, means the cache can be extended. So these are the things can be there, how the bus can be responded within the cache memory. So here we are having the snooping protocol. The snooping protocol, the finite state machines can be used, and here the snooping operations can be handled with the use of the write back cache. The write back cache is very important. After performing the cache operation, every cache data has to be updated to the main memory with the use of write back cache. Okay. So and how it can be possible is, it snoops the cache controller, snoops the bus and check whether what is the recent read and what is the recent write. So after the recent write, it can be updated. And second one is memory block. Here memory block we are having the three different things. First one is shared. Here we clean all the caches and update the data in the main memory. And exclusive dati, here the cache memory, the data bit only considered and now not in any caches. The same way the cache also contains three blocks. The first one is shared block. The block can be read, and second one is exclusive. We can read and write also read, otherwise write can be possible. Then invalid, there is no data can be available in the invalid. So this is the things can be there. Here this is the write back state position, and based on the CPU request for the each catch block. The CPU requests the data to the catch block. For here we are having the three things: invalid position, shared position, and exclusive position. Or the invalid, there is no data can be performed. The shared, we can perform the read operation, read only can be performed. The exclusive, read or write can be performed. Okay, here we are having the first, when we issue the CPU read, we are going to take the data. If suppose the data can be available, we can get the data. Here two things can be very, very important. First one is hit, second one is miss. If suppose when we see the data is available, we can say that is a hit operation. If the data cannot be available, we can say it's a miss operation. So here there is from invalid to valid. The first we are going to take the CPU read operations. If the data can be available, we can get the hit operation. If there is no data on the thing is, we can issue the miss operations. The same way the write operation, the write can be issued. If there is a write is there, we can get the hit operation. Otherwise, we can get the miss operations. The same way from the shared block to exclusive also, we are going to issue the read and write operation. The data can be available, we can get the read CPU write, otherwise we can get the miss operation. The same way we can get the data on the bus request also. Here also we are having the three things: invalidate, shared, and exclusive. Here also the same thing, we are going to ask a data. The data can be available means we can get the hit operations, otherwise we can get the miss operations. And the same way read miss and write miss can be occur. The same way the write operations also can be performed. The same way the block replacement also can be performed with the use of finite state machine. Here the state machine requires the catch block. The catch block also we can get the read operation and write operation, and the miss operations also can be get hit, and we can get the miss operations, and exclusive operations also can be get. Both the catch blocks, CPU blocks, and contain the overall finite state machine diagrams can be placed here. This is the example. So how it can be things, same thing can be with the use of examples can be shown in this diagram. We are having the initial cast states can be taken in the A1 and A2, and how it can be shared. And in the symmetric, snooping protocol, we can get performance can be checked with the use of two measures. First one is true sharing and another one is false sharing measures. If suppose the P1 and P2 use the same data x1 and x2, if P1 access the x1 data and P2 access x2 data, if suppose the mesh can be occurred in the P1, we can say there is a true sharing mesh. So if suppose the P1 cannot use the data x2, then we can say it's a false sharing mesh. There is a things can be there, and through the communications we can get the true sharing measures, and the invalidations we can get the false sharing measures. This is the example. Here we are having x1, s2 in the same catch block, and processor P1 and P2 both uses x1 and x2. For example, P1 write the data, write x1, okay, then we can get the true miss because we are going to invalidate the P2. The P2 is invalidated. If suppose the P2 read the x1 but it not using the x1, so it is a false miss because x1 is not relevant to P2. The same way here we are using the write x1, we have the false miss on x1 because the P2 cannot use x2 in this operation. The same way P2 issues the write x2, here the P1 cannot issue the using the x1, so we can get the x1 as relevant to x2, so we can get the false miss. The same way P1 we are using the read x2, the true miss can be occur. When we true miss can be occur, we are going to issue the invalidate on the another processor. This is the example of the performance between the true sharing and false sharing measures. So here how we are going to increase the 1 to 8, here first CPU, and here only one processor can be used here, the 2 processor, 3 processor, 4 processor and 5 processor. When we extend the processor, definitely the meshing also can be extended. So next we are discussing about the distributed memory machine. Already I told the distributed memory machine, there is no common memory can be there. Here every processor can have a memory. Here this memory contain the directory and cache memory and interconnection networks can be there. And here the cost effective approach, because every time when we use a large memory set tedious task, so it's a very cost effective approach, reduce the latency. And what is difficulties in this one is the communication is very difficult, and the directory protocols can be used. The directory protocols can be enabled with the use of communications messages. Here the communication, here like a snooping protocol, here also we are having the states. Here the snooping protocol we are having a 3 state, one is invalidate, another one is a sad state, another one is a exclusive state. Here we are having the in this directory protocol you are having the shared state, one processor have the data, and uncatched state and exclusive state, the name is different. And here we are having to have the writes to non-exclusive data, that is called as write miss also can be occur. So directory protocol, here we are having the 3 nodes. So what is the first here? Here we are having the 3 nodes. The first node is local node. The local node issues the request, and home node, where the memory locations of an address resides or not. And next one is remote node. 3 nodes can be there, because when we have the directory, 3 nodes: local node, home node, and remote node. And here we are having P is a processor number, A is the address number. So in the directory protocol, already I told about the directory protocol, everything can be performed with the use of messages. Okay, and we are, for example, what are the message type? The first message type is read miss. This is the source and destination. Local cache you are using. Here the home directory, and the directory contains the local node, home node, and remote node. If suppose I are issuing the processor, and we are having the, already I told A is the address and P comma A. So the processor P wants to read at address A. If suppose the data is present, we can get a hit. The data is not present, we can get a read miss can be occurred here. The same way write miss. If suppose the processor wants to write the A data, but that data can be accessed by another processor, so we cannot write the data. At the time the write miss can be occur. And another message type is invalidate. So if suppose the shared data processor P1, P2, P3 can using the data, means one processor can invalidate that processor because it wants to update the data. At the time the another process cannot get the data, that message is called as invalidate. And second one is fetch. Fetch is nothing but the remote data can be taken by the processor, that message is called as fetch. And fetch or invalidate, here the block sent to the home directory or remote directory, at that time we can fetch or invalidate messages can be given. The next one is data value replay. If suppose we are going to take a data to the home directory, at some time we can get that the data is missed, means we can get the read miss. So after the data available, we can get the replay back, that is the data value replay back. The same way we are having the data write back, the invalidated copies can be updated, after invalidated can be removed from the processor. So this is state transitions things. The same things like a snooping protocol also, the directory protocols can have the things. So here we are having the things invalidate, shared, and exclusive. And here also we are having the messages can be sent between the each and every processor. When the messages can be sent between the processor, definitely we can get the problem. The communication is very, very difficult. So this is the directory. This is the shared architecture. The shared architecture we are having the invalidate, shared, and exclusive. The same thing can be in the distributed architecture. We are having the uncatched, shared, and exclusive. And uncatched, there is no data can be there. Shared, the data can be processed with the use of read-only processor, read-only operation. Exclusive, we are having the read or write operation. The same way the read miss can be occur. Here the write miss can be occur. So whatever the messages we have seen in the diagram, the same thing can be seen here also. So this is the example for directory protocol, how the cache states can be updated. Here we are extra, other than the snooping protocol, here we are using the directory structure. This is the parallel program example. So already we are discussing the multiprocessor programs. So all the multiprocessor, when we use the shared data can be handled with the use of two variable. One is lock variable, another one is unlock variable. So what is the use of lock variable is, if suppose the processor P1 accessing one data, it can be locked by the processor P1. If suppose the P2 wants the same data used by the processor P1, when the unlock given by the P1, then only the processor P2 will take the data. So that is the things can be given here. Here we are having the locking data and unlocking data, and everything can be involved. It's a parallel program example. And up to this we have discussed about what is the parallel architecture, how the classification based on the Flink's taxonomy, and how the classification based on the memory management. Here what are the issues can be raised when we use the multiprocessor? The first one is synchronization. So what is synchronization? Because different processor can use the same data, definitely we can get the different data. Already we have discussed in the example, U value can be 4 in one place, 5 in another place, 7 in another place. So we can get the misinterruptions can be there. So that is the so when we use the shared data variable, the U is a shared data variable, for example, the synchronization is very, very important. So how the synchronizations can be handled means the use of three things. The first one is uninterruptible instruction. That is, the atomic operations can be used. The second one is user level synchronization, and third one is barrier level synchronizations. The three things can be used. First one is atomic exchange. Here every single operations can be performed. For example, the shared data can be handled. If suppose one processor can use the shared data, that data can be used with a synchronization variable. So the synchronization variable can be used with the use of 0. 0 means the synchronization variable is free, because the processor, any variable cannot be used by any processor. So every variable can have the synchronization variable. If the synchronization variable is free means there is no problem, any processor will take the data. If suppose the synchronization variable, the flag variable can be set 1 means because already that variable can be used by some processor. So the P2 wants to wait to whether the variable is available or not. For that purpose we are having 0 and 1. The next operation is test and set operation. So first one is we go and check the flag variable. The flag variable is free means we will check the variable, we can utilize with the processor. The flag variable is higher means we have to wait the things. Another operation is test and set. We are going to test whether the variable free or not. It is free means we can access, otherwise set the variable. And third one is fetch and increment. So here the memory location is automatically incremented. If suppose 0 means the variable is free, otherwise it can be 1. And next one is spin lock. Spin lock is nothing but here again and again going to check the variable is free or not. So for that purpose, here the loading the variable or R2 variable can be loaded with the 1 value. Here exchange the variable R1 with the R2, and we are going to check whether the branch is not equal to 0. So the lock it variable can be used. Whether go and check the variable whether it can be available or not. If it is available based on the synchronization flag, we can utilize the variable, otherwise we cannot utilize the variable. So for that purpose we are going to introduce the here the problems can be arise, the catch coherence problem arise. It can be solved with the use of these things. Here we are loading the load with the variable and go and check whether it can be free or not. If it is already locked, we are going to wait, otherwise we are going to utilize the problem. So example of a test and set, load the variable R2 with the 1 and exchange the variable locations for R2 with the locations, and we have to check branch is not equal to 0 or not. This is for locking it, this is releasing it. Already I told in the multiprocessor, the shared data can be accessed with the use of two techniques. One is locking, another one is unlocking. The locking can be done by this block and the releasing can be done by this block, unlock block. The same way test and set, the test and set examples also already explained, the same thing can be given here also. The store conditional, again we are using the another variable also can be used. Using the extra variable we are going to check the synchronization, the shared data can be there or not. And another example for another synchronization variable is load, linked and store conditional. So load linked is nothing but we are having the load and store. Already we know load and store is both operations, very important operations. The loading is nothing but we are going to placing the data in the memory and starting the execution. Storing is nothing but after performing the operation, the data can be stored in the main memory. The load and store is very important when you perform any operations. So go and check the variable whether the shared data is there or not, and based on the shared data availability, we are going to apply the load, linked and store conditional operation. So load linked issue, the load can be locked, and the store conditional is nothing but after that it can be released. So for that purpose we are having the things, we are moving the data R3 to R4, and load linked can be used, store conditions SC can be used, and with the use of this branch and store operation, it can be released. The same way you are having the fetch and increment also can be performed. Another one important synchronization is barrier implementation. With the use of barrier implementations also, we can remove the shared catch coherence problems can be present here, and for that purpose we are constructing the separate block, barrier block. If suppose the processor P1 accessing the data, it issues the barrier. When the barrier can be released, then only the processor P2 will access the data. So for that purpose we are having the barrier, and barrier also we are using the lock and lock variables. So this is an example, we are having the sleepers and counters can be used. The last topic is memory consistency. The memory consistency also we can get a problem when we use the shared data can be there. So what already first we have discussed the coherence problem, second we have discussed the consistency. Coherence problem already I told, with the same data misprediction of data can be there, that is called as coherence. Consistency is nothing but when we issue the read and write operations, we have to take the recent write operations. So we cannot get the previous, we cannot take the previous read operations. At that time we can get the consistency problem. That is catch problem, coherence problem is different, consistency problem is different. In the consistency, for example, when you take the, this is the processor P1, this is the processor P2. The processor issues the values A is equal to 0 and A is equal to 1, and here we are giving B is equal to 0. The same A value and B value also can be used by the processor P2 also. B is equal to 0, B is equal to 1 if A is equal to 0. If suppose processor P1 and processor P2 wants to access the same data at the time, we cannot get the data because the processor is using A's data and it will check the B's data. After releasing A's and B's data, then only the processor P2 will act. Otherwise we can get the data cannot be, the recent write data cannot be get. So for that purpose we can get the impossible transactions can be there in L2 time. At that time we can get a hazard problem solving. There is no operations can be performed. For example, if suppose we want to, for this one the example web page, we want to download any data, at that time we cannot get the downloading of data. So there is the due to the consistency problem only we can get the things. So at that time how it can be there, because the processor P1 updating at that time, it issues the write invalidate to processor P2, then only the problem can be solved. So after the processor P1 operation has been completed, it has to issue the write update. So the write, after the completion of write invalidate, then it issues the write update, then only we can get the problem can be solved. How it can be there is with the use of consistency. That is a sequential consistency. What is the sequential consistency is, whatever executions can be there, it can be performed sequentially. The first processor if issues the write invalidate, the processor P2 has to wait, and again the processor P3 has to wait. So likewise it to be continued. Likewise relaxed consistency also can be there. Likewise many consistency problems can be there to solve the consistency problem. Here the same way we are having the things, how the problems can be solved is, so for that purpose we are writing the data, reading the data, we are going to lock and release. The lock and release is for lock process we are getting the acquire, and release process we are having the unlock the data, and we are having the same way several consistency models can be there, relaxed consistency, strict consistency. Likewise many consistency models can be there to avoid the consistency problems. So for that purpose we are having the RAR, WAR, read after write, WAR, write after read, and RAW, write after read after write, and WAW, write after write. To give all these things, then the consistency problems can be solved. Thank you. So here what are the things we have discussed in this video lecture is what is multiprocessor, why we are using the multiprocessor, and due to multiprocessor how the thread level parallelisms can be involved, and the parallel computer classification based on the Flink's taxonomy, and the parallel communications based on the memory management, symmetric and directory architecture we have discussed, and the two problems we have discussed. First one is coherence problem, catch coherence problem we have discussed, then the catch consistency problem we have discussed. So after that the issues of synchronization and memory consistency problem we have discussed. To do with the use of this lecture we can able to understand the parallel architecture. Thank you.